Let's take some notes. So, multiplying matrices is where things get crazy. You can only multiply two matrices A and B when the columns in A are equal to the rows in B. When you multiply a matrix A, which is an M by R, and a matrix B, which is an R by T, the resulting matrix AB is an M by T matrix. So we have columns then rows. No, rows then columns. M rows by R columns. When we're looking at our matrix, M is the number this way, R is the number that way. How many columns we have has to be the same as in the other one. There are R rows and T columns. So notice that the rows and columns here match. So in this matrix, this way has to have R rows by T columns. They have to have the same number because when we multiply the matrices, we take the sum multiplying across the corresponding column and down the corresponding row. So we go across this way, so we hit every single one of these, while we go down this way, pairing the ones from the first matrix with the one from the second matrix. So you would pair this one and this one together. You would add to that the second one and the second one down, the third one, and the third one down, the fourth one over, and the fourth one down, the fifth one over, and the fifth one down. You would multiply all those together and you would take their sum. You would add them all together. Crazy! So we multiply across the first one and down the second one. So we multiply A times E and B times G. And we add those together for our first entry. Then we multiply the first row by the second column. A times F and B times H. We sum them together. Then we multiplied the first row by both of the columns. So now we have to move to the next row, the second row. And we multiply the second row times the first column. C times E, D times G, and add them together, take their sum. And then lastly, we must multiply the second row by the second column, C times F, D times H. And we take their sum for our last entry in our new matrix. So let's just try it here a little bit. Let's multiply x times y here. So we want 5, 2, negative 1, 3 multiplied by 2, negative 4, 7, 3. So we're going across this one and down that one. 5 times 2 is 10, plus 2 times 7 is 14. We now do 5 times negative 4 is negative 20, and 2 times 3 is 6. Negative 1 times 2 is negative 2. 3 times 7 is 21. Negative 1 times negative 4 is positive 4. 3 times 3 is 9. Then you actually have to take the sums. So we have 24, negative 14, positive 19, and 13 as our matrix we get from multiplying the matrices x and y together. So let's multiply y times x. 2, negative 4, 7, 3 times 5, 2, negative 1, 3. We're going across this one and down this one. So we have 2 times 5 is 10. Negative 4 times negative 1 is 4. 2 times 2 is 4. Negative 4 times 3 is negative 12. 7 times 5 is 35. 3 times negative 1 is negative 3. 7 times 2 is 14. 3 times 3 is 9. We then actually take the sums, and that's our multiple. 14, negative 8, 32, and 23. What do we notice about these two matrices? We want to notice that they are not the same. X times y does not equal y times x. Matrix multiplication is not able to just be switched around. You get very different matrices depending on which way you multiply. So that's very, very important. Matrix multiplication is not commutative. You can't switch them around. So if we're looking for A times B, then we have a 3 by 2. We have a 2 by 3 times a 3 by 2. So these two have to match, while these two will tell us how big the result is. These two have to match because you have to have the ability to go across this one and pair everything with something you go down that one for. So those are the dimensions of AB. The result will be a 2 by 2 matrix. Results in a 2 by 2. Whereas if we do BA, we have a 3 by 2 times a 2 by 3. So these two match, and our result is a 3 by 3. So if we take 3, 1, 2, 7, negative 3, 4, and we multiply it by 2, negative 2, 3, negative 1, 1, negative 4, what are we going to get? So across the first row and down the first column, we have 3 times 2 is 6, plus 1 times 3 is 3, plus 2 times 1 is 2. Moving over, we have 3 times negative 2 is negative 6, plus 1 times negative 1 is negative 1, plus 2 times negative 4 is negative 8. Now the second row times each column. 7 times 2 is 14, plus negative 3 times positive 3 is negative 9, plus 4 times 1 is 4. And lastly, 7 times negative 2 is negative 14, negative 3 times negative 1 is positive 3, and 4 times negative 4 is negative 16. So taking our sums and moving over to do B times A. 2 times 3 is 6. Negative 2 times 7 is negative 14. Moving over, 2 times 1 is 2, plus negative 2 times negative 3 is positive 6. Moving over, 2 times 2 is 4, negative 2 times 4 is negative 8. And now we reset and move down. 3 times 3 is 9, plus negative 1 times 7 is negative 7. 3 times 1 is 3, plus negative 1 times 3, negative 3 is 3. Whoops. 3 times 2 is 6, plus negative 1 times 4 is negative 4. Moving down in the first and 1 times 3 is 3, plus negative 4 times 7 is negative 28. Moving over. 1 times 1 is 1, plus negative 4 times negative 3 is positive 12. Moving over. 1 times 4 is 2, plus negative 4 times 4 is negative 16. We're going to add all those together. So a little more clear here that the order of multiplying the matrices is super important. In one case, we get a 2 by 2 matrix. Switching it around, we get a 3 by 3 matrix. Hugely different. Very important to understand how we multiply these things together. So with the order mattering, it turns out that we can move parentheses around. So we do have an associative property. It doesn't matter if you do those two first or if you do those two first. When you're multiplying a scalar in, it doesn't matter if you multiply the matrices together and then the scalar in, or if you multiply the scalar in and then multiply by the last one, or if you multiply the scalar times the last one and then multiply times the first matrix. Any which way you go. The ones that are a little weird are the distributive properties, because you have a matrix being distributed here. So you're left distributing. Both of these have to be on the left. Whereas down here, you're right distributing, and they have to be on the right. Since the order matters, that part matters also. That's our matrix multiplication.